Okay, let's start our lecture today. Today I will sum up the polynomial topics on polynomial, which we finished on last Friday. Today we will put everything together, and it should take like around 1 hour. And then from there we will start conceptual foundation for rational function. So whatever the theory things that we need to know, we do them today, and then tomorrow we will sum it up. When I say sum it up, basically put all the pieces together. Okay, and yeah, tomorrow also after we finish up chapter 3, rational function. That's the last section of chapter 3. I will go on to 4.1 and 4.2. Oh, I may do a bit of variations. 3.6. I may do a bit of variations, but that's supposed to be an easy stuff. Okay, I strongly recommend you to start looking at my old lecture videos if you want to speed up and study from my old test 2. As I remember, my old test 2 actually ends at 4. Let's see, it ends at 4.4 as I remember. It ends at 4.4. I don't think it is 4.5. Yeah, I think it ends at 4.4. Okay, so I think on Wednesday we should be done with the material for test 2, and your test 2 will be this Friday. So test 2 will be this Friday, July the 15th, and we will cover the last section of chapter 2. What's that? It's 2.7 as I remember. So the material will be section 2.7, 3.1 to 3.6, 4.1 to 4.4. Okay, that's the material for your test 2. Now, okay, we will go back to 3.4, section 3.4, part B. The question is, let's say question number 22 first. Number 22. This is actually an easy question. The question is find all the solutions. Find all the solutions of this equation: 12x cubed plus 8x squared minus 3x minus 2 equals to 0. This is actually something you can do even before chapter 3. Why? Because I believe this is something we can solve by factoring. Yeah, we can solve this by factoring. I can take 4x squared out, and then minus 3x plus 2, and then so on and so forth. Okay, I believe the answers are negative 2/3, x equals to negative 1/2, x equals to 1/2. Okay, now the thing is, in this course, in this section, actually our main topic is graphing. Okay, so not only find the the solutions for an equation, but it's more into let px be 12x cubed plus 8x squared minus 3x minus 2. And then the question we need to answer, the first one, the domain, of course that one is easy. That's all real numbers. And then how about the y-intercept? That's 0, negative 2. Okay, and then for x-intercepts, you basically do what we did here, right? Therefore, we get negative 2/3, 0, negative 1/2, 0, and 1/2, 0. And of course, we can also talk about the Starter straw sign, right? Or rational zero theorem, so on and so forth. Okay, a lot of things we can do, but one thing we can definitely do right now, right away, is to sketch the graph. When you sketch the graph, you don't need to sketch it to scale, but you need to denote the coordinates. Okay, so for example, this one here, this x-intercept, that's 1/2, -1/2, -2/3. Yeah, you don't need to make it to scale. Okay, and then this is degree of what? Degree of 3. This is degree of 3, leading coefficient positive, so it goes this way. Yeah, and each 0, as you can see, each 0 is a simple 0. Okay. But this question is not interesting because it's something we can do to find the x-intercept, something we have been able to do since even before we start this chapter 3. Now, once the polynomial gets to higher degree, let's say degree of 4, degree of 5, then basically it's not factorable. Okay, so let's take a look. For example, I picked number 24, but I modified that. Instead of solving the equation, which is basically part of the procedure later on. Okay, I will remind you what do we do if we need to solve for that equation, but I will see that from an even higher dimension. It is by seeing that as a polynomial. Let px, the polynomial function, be x to the 4th minus x cubed minus 9x squared plus 3x plus 18. Part A, the domain. A polynomial always have a domain all real numbers. And then part B, according to the Descartes rule of sign, how many positive zeros, how many negative zeros. A number of positive zeros, we see how many times the number changed. 1 time, none, another 1 time, no. So it's either 2 or 0 positive zeros. Now, how about how many negative zeros? Now, to find the number of negative zeros, I need to first see the p negative x. Okay. Now, when we replace x by negative x, we are basically reflect that with respect to the y-axis. And then, so what you do is you reflect that with respect to the y-axis, and you will repeat the procedure we did earlier, where we want to see how many times the sign changes, the number of variation of signs. So p negative x is x to the 4 plus x cubed minus 9x squared minus 3x plus 18. The number of times the sign changes, 1 time, 2 times, 2 or 0 negative zeros. That's the Descartes rule of sign. How about rational zero theorem? What rational zero theorem says? Find the possible rational zeros using rational zero theorems. Yeah, the thing is, even if they have rational zeros, we don't know yet what, who they are, what they are, right? And rational zero theorems being used to kind of like limit our options. Okay, that would be plus minus the factor of the constant. Okay, the factor of constants are 1, 2, 3, 6, 9, 18. Actually, not that 18, but this 18. So this 18 to be more precise. Okay, not that 18. I need to erase this. Not this 18. Not this 18. Not this 18, but from the original polynomial. Even though they will be just the same. Okay, now and then on the denominator, there will be the factor of the leading coefficient, which is just 1. Okay, now make sure that all the coefficients of of each terms are integer. Then we can use this rational zero theorems. If not, then you factor that fraction out. Okay, so the rational zeros, let's call that C, then that would be plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 9, plus minus 18. Those are the possible rational zeros. Okay, then the next one, then use that to find those zeros. Find the zeros of Px. Now, this is the same tool. This is basically the same tool. Find the roots or the solutions of that polynomial equation of x to the 4th minus x cubed minus 9x squared plus x minus 3 equals 0. Okay, that's the, am I copying the right one? No. Plus 3x plus 3x plus 18. So plus 18. X to the 4th minus x cubed minus 9x squared plus 3x plus 18. Yeah, so finding the zeros of this Px is basically finding the solutions of that equation. Okay, so here's the thing. We cannot do factoring. We only have the candidates. What we can do is we do guessing game. Okay, now keep in mind that somewhere in between we have intermediate value theorem to help us. So here's what I will do. Here's what I will do. This is my scratch work here. And I will only show on my paper in your quiz, for example, the one due tomorrow. Okay, you just show the zeros. Okay, you don't need to show your scratch work. Okay, so I will use synthetic division. I know that the y-intercept is what? The y-intercept is 0.18. Huh? Okay, now let's try when x equals to 1. So when x equals to 1, that's 1, negative 1, negative 9, 3, 18. Okay. Actually, you will see P1 equals to the sum of the coefficients. Yeah, for P1. Because you replace the x by 1, right? So when you replace the x by 1, you basically add the coefficient of this. Okay, yeah, I think the answer will be 12 later on. But let's work it out so that you see what I mean. Okay, let's is 1, this is 1, this is 0, this is 0, this is negative 9, negative 9, negative 6, negative 6, positive 4. Okay, so 1 is not a 0, so 1 is not a 0 here. So you don't need to put this in your paper. Okay, and then let me try 2. You can try 3 right away, but let me try 2. So I start a new. I start a new phase here. So 1. This is 2. This is 1. This is 2. Negative 7. Negative 14. Negative 11. Negative 22. That's negative 4. Now we see that so 2 is not a 0. Of Px. But from here we see something strange. Notice that P1 is positive, is 12, while P2 is negative. So there is a 0 between x equals to 1 and x equals. Okay. Now, according to what we have here on the Sartre sign, we should have 2 positive zeros. Now, we found one of them, but that one is not a rational number. Okay, because when you see the list here, there's no rational number in the candidate that is between positive 1 and positive 2. You see that? Okay, so that's how we know that, you know what, there's a 0 between 1 and 2, but there's on our rational zero theorem, there is no rational 0 between 1 and 2, no candidate. Okay, so we need to look for only one positive integers now. Okay, we just need to look for another one positive integers now that give us the 0. Okay, because we know one of them is between 1 and 2, and that's irrational. Okay, let me try 6. Let me try 6, 1, negative 1, negative 9, 3, 18. And let me try 6. Let's see what happens. 1, 6, 5, 30, only 1. This is 1.6. This is 1.9. This is big. This is big. Now then from here you see that P6 is positive again. So you see, then there's a 0 between 1 and 2. There's also a 0 between 2 and 6. Okay, as if I'm saying here, it's like when x equals to 1, that's positive. When x equals to 2, that's negative. When x equals to c, that's positive. So there must be a 0 somewhere in between here and a 0 somewhere in between here. Right? Now, for that reason, then, is there any rational number between 2 and 6? Is there any rational number between 2 and 6? Yes, 3. Let's try 3. I could have tried 3 earlier, but I purposely used 6 so that you see how we use intermediate value theorem to detect a 0 in between. Even if we don't get a 0, like 6 is not a 0, right? But I can use that to detect somebody nearby. So let me try 3. 1, negative 1, negative 9, 3, 18. It is. Yeah, so from here we see that 3 is a 0. 3 is a zero of Px. Now, because 3 is a zero, I will copy that in my formal work. Okay, I will copy that on my formal work. I have that feature here, but when you do the handwriting, then you need to copy whatever you have from your scratch paper to your test or quiz paper. Okay, so I'll put it here. Now then, from here we go on. Basically the polynomial px now have become x minus 3, that's degree of 1. The polynomial is degree of 4, so when I divide by x minus 3, now I have degree of 3. Okay, now then from here you go on again, see again if you can reduce this further. Actually, if you think about this, you can already do grouping, factorization by grouping from here, right? Okay, now we see there's only one change of sign right now. There's only one change of sign right now. And that one change of sign is the one that we say irrational. So even if we can find an irrational here, even we know there's a zero between in the positive side when x is positive, right? But we know at the same time it will be irrational. So we will not try to find it anymore. Let's switch gear to the negative side. Okay, now let's switch gear to the negative side. Let's try to continue. I will continue dividing from here. I will continue dividing from here. I already reduced it, so I don't start from the very beginning. I start from the reduced polynomial. Okay, I will start from reduced polynomial. 1 to negative 3, negative 6. And then try, for example, do the guessing. You can try negative 1. When you try negative 1, 1, 1, 1, 1, 4, this is 4, that's negative 2. So we see that P0 is 18, P0 is 18. P0 is 18, but P negative 1 is negative 2. As if I'm saying like this is a number line, 0 is positive, that negative 1 is negative. So there must be a 0 in between, right? But again, between negative 1 and 0, there's no rational integer, rational zeros in our list. There's no rational zeros in our list. Unless I count it wrong, but let me see. Yeah, there's no rational zero in our list. Yeah, there's no rational zeros. So it must be irrational in between there. Okay, so from here we say that negative 1, not only that we know that negative 1 is not a 0, we also know that there is one irrational 0 between negative 1 and 0. Now let's try again then. So negative 1 doesn't work. I still start from that 1 to negative 3, negative 6. I know negative 2 will work, okay, because I did the grouping in my head. So negative 2 is a 0. I will continue from here. Okay, negative 2 is a 0. So we can now rewrite our polynomial as x minus 3, x plus 2, or x squared minus 3. Now you see the last part here, I can factor it further, right? So that's x minus 3, x plus 2. You know what? Let me just solve it first. So x squared minus 3 equals to 0. So I get x squared equals to 3. X will be plus minus radical 3. Okay, so the zeros are x equals to 3, x equals to negative 2, x equals to radical 3, x equals to negative radical 3. Each one of them with multiplicity of 1. Or you can simply say m equals 1. I will understand. Okay, I just feel strange that from here, I mean the last one here, I feel strange. Oh, you know what? No, 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 no. I think I should use P star here. P star negative 1. This is our P star. Px star. It's negative 2, while P star 0 is actually not 18. That's negative 16, negative 6. So no, there's no 0 in between. Okay, there's no 0 in between. But you see that our radical 3 here, it's between 1 and 2. If you use your calculator, radical 3 is 1.7 something. Okay, that's 1.7 something. So this guy here actually refers to what we have here. Okay. And notice that according to our Descartes' rule sign, we do have now 2 positive zeros and 2 negative zeros. Okay, and lucky that we don't have any complex zeros. Now it could happen though, it could happen. Okay, it could happen. Now that's for number 24. Actually, so with this then we also find the roots of that equation. The same method basically. To find the roots of that equation is the same to find the zeros of Px. Okay, so you set one side equals to 0 and call that a polynomial. Now usually I have a follow-up question. For example, what question is that? That's part D. So part E. So find, write down the x and the y intercepts. The y-intercept, we have done that earlier. That's 0, 18. The x-intercepts are negative 2, comma 0, negative radical 3, comma 0, radical 3, comma 0, and 3, comma 0. And then what else? Find the far end behavior. Far end behavior, it follows the leading term. The leading term is x to the 4. So that's the leading term. Is positive x to the 4, so it must be top. Okay. Or in limit notation, as x goes to infinity, px will also go to infinity. When you go very far to the left instead, x goes to negative infinity, px will be equal to going to also infinity. That's the far end behavior. I may ask you for some strange reason, find p negative 4 by using synthetic division. basically I use remainder theorem. Okay, so I have, what's that, 1 and then negative 1, negative 9, 3, 18, negative 9, 3, 18, 4, 1, 4, 5, 6, 11, 4, 4. This is negative 41, 41, this is positive 164, so this is 182. So P negative 4 equals to 180. Now finally, part H, sketch the graph. I will sketch that without sketching it to scale. Just make sure you put in your x-intercept, your y-intercept, and the up, down, so on and so forth. Okay, so my x-intercepts are radical 3 and then 3, negative radical 3 and then negative 2. Okay, and then it's top, so it will look like this, the far ends behavior. Now what happened in between? So it will be all simple zeros. So when it cross the x-intercept, it will cross as a linear. Like it cross just basically like a line. And this is positive 8. So the x-intercept and y-intercept, you put that notation. Okay, write it like this. Write it like this. Not just a dot, because we don't draw it to scale, right? So you need to put that in there. Okay. Now that's for number 24. Now let's see number 26. Number 26. Let Px, I modified the question. Okay, let Px equals to, if all you need to do is actually finding the zeros, if you only need to do is finding the zeros, then you don't need to call that Px anymore. You still can, but you don't need to, right? But you see that all the procedure that we learned in the previous section, 3.1 up to 3.3, even 3.4, it's all directed, pretty much all of them directed to find the x-intercepts, and using that x-intercept, we can write it in linear form. Or did I ask that question? Okay. Linear factor. Maybe I write it here, I insert it here, insert. Write Px as linear factor. So you will say Px equals to x minus 3, x plus 2, x plus radical 3, x minus radical 3. Okay, that's the linear factor. Here, Px, I go back to number 26, Px equals to 3x to the 5th. Yeah, solving for that equation is basically finding the zeros, and using the zeros, knowing that they are, if they are real numbers, that will be translated into our x-intercepts. Okay, so instead of just finding the zeros here, the roots of the equation, we go even further to graphing it. Okay, without graphing calculator, of course. Now, don't rely too much on your graphing calculator. Please, 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 please. I know some of you may use graphing calculator at home. When you do the test, it's not helpful. It's not helpful. You will see that your graph looks so wrong because If you actually graph this on your graphing calculator, it will just look like lines like that, you know. Okay, no, don't do that. It is possible that you are actually looking at a blank screen, you know. Okay, so please don't do that. Okay, so let's see what the Scattershore sign says. Number of positive zeros are 1, nothing, 2, nothing, 3. One here, another one here, another one here. So the number of positive zeros will be 3 or only 1 positive zeros. Okay, now how about number of negative zeros? Then I need to see what will P negative X look like. Okay, now let me just cut one step, but you still need to know, show the next one here. Basically, if it is odd exponent, you change the sign. Even exponent, you don't change the sign. Because negative x to the power of to even power will still be just the same sign. Okay, it's still positive x. I just want to change this. We will see that there will be one change of sign, there's another one change of sign. So there will be 2 or 0 negative zeros. Okay, now how about rational zero theorems? According to rational zero theorems, the possible rational zeros are a factor of 6 and a factor of 3. Okay, factor of 3 on the top and the factor of 6. Now you don't need to worry about the plus minus because the sign, because we already take care of that here. Okay, but I still need to spell it out though. I need to write it down. This will be plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 1/3, plus minus 2/3, plus minus 3/3 is basically 1, so I don't want to count it anymore. It's the same to this, it's the same to this. And then the last one will be plus minus 6/3, but that's basically 2. Okay, so from this list we see we have 12 candidates. We have 12 candidates. Okay, we have 12 candidates. So then let's start find the zeros. Find all zeros of EX, including the complex one, if any. Now then, on my right-hand side here, I will use that as my scratch paper. Now, in your test or your quiz, you don't need to show me your scratch work. Okay, the one you need to show me are only those zeros, only the numbers that give you the zero. Okay, so this is my scratch paper. But I show you my scratch paper here so that you see the way I think. Okay, which is more important though. Okay, then I have 3, my px is 3x to the 5th minus 10x to the 4th minus 6x cubed plus 24x squared plus 11x minus 6. Okay. So P0 is -6. That's the y-intercept, by the way. Now, how about P1? P1, you will see we just add the coefficients 3 minus 10 minus 6 plus 24 plus 11 minus 6. Oh, do you think that will be positive or negative? It will be positive, huh? So 27, 38 minus 22. That's positive 16. Right? But you see that between 0 and 1, the sign changes, right? The sign changes. You notice that? So by intermediate value theorem, let me draw it here. So when x equals to 0, the value is negative 6. When x equals to 1, the value is positive. So there must be a 0 in between by intermediate value theorem. Now let's look at our list. When we look at our list here, between 0 and 1, there are two positive rational zeros, 1/3 and 2/3. So let's try either one of them, or maybe both. We don't know. Okay, yeah. Let's try either one of them. So I will try to find if 1/3 is a 0. Either 1/3 works or not, you will see again later on. Okay, so this is 3, negative 10, negative 6, 24, 11, negative 6. Oh, by the way, be very careful if there's any jump here. You see the degree is degree of 5, 4, 3, 2, 1, constant, right? Okay. Make sure that if you have a jump of degree, you will put a placeholder 0. Okay, this is 3, 1, negative 9, negative 3, negative 9, negative 3, 21, 7, this is 18, 6, 0. Yay, there's a 0. Okay, so now I can put that on my formal work, so formal paper, 3, negative 10, negative 6, 24, 11, negative 6. What I do right now, I'm supposed to copy that, but let me just redo it again in case I make miscomputation. Okay. Now notice that I can factor a 3 out, right? Do you notice that? I can factor a 3 out now. So basically, if we look at this polynomial right now, we can say it this way: px equals to x minus 1/3 times 3x to the 4th, degree of 5 originally. Now, because I divide by x minus 1/3, I get degree of 4 minus 9x cubed minus 9x squared plus 21x plus 18. Now, I will factor the 3 out, okay? I will factor the 3 out. That helps us simplify the computation later on, though. Okay. Now then we now look at this. So I now have 1, negative 3, negative 3, 7, 6. Notice that if I apply rational zero theorem here, okay, then the candidates for rational zeros will be 1, 2, 3, 6 over only 1. So once I get that, in this case, once I get that 1/3 as a 0, I can now update this list. Okay, and when I update that list, I actually knock off 1/3 and 2/3. I only take that 1/3 out in this case, right? Okay, so once I divide by that x minus 3 and factor that another 3 out, the candidate only this, which translates into plus minus 1, plus minus 2, plus minus 3, plus minus 6. Notice that we don't have 1/3 as a candidate anymore. We don't have 2/3 as a candidate anymore. Is it okay? Now, let's go on. So all the theories that you learned on Friday, however good they are, the difficult part is actually how to put things together and make things work. Okay, so you need to know all those theorems and kind of like keep on updating your information. Okay, and then we tried one earlier. So if it didn't work earlier, it won't work right now, right? So I will not try one anymore. Even though I know from here, I still have possibly 2 positive zeros. I already get 1, right? Original 3 or 1. Because I get 1 out, I get either 2 or 0. Let's try again. Let's try again. Let's try 2 round. 1 doesn't, it's the positive zeros, possible positive zeros are 1, 2, 3, 6, on the positive side. But we already tried 1 and it didn't work. If it didn't work very early, it won't work right now. Okay, let me try 2. You know what? Let me try 3 or 6. Let me try 6 right away. 1. This is 6. This is 3. This is 18. This is 15. This is 90. This is 97. This is very big number. Very big number. So 6 is not a 0. So 6 is not a 0 of px. Okay. But there's one more thing I want to teach you, something I didn't show you last time. Boundedness theorem. Boundedness theorem. Boundedness theorem says this. Boundedness theorem. If you know it, that's good. If you don't know it, you're fine. Okay. If C is positive and the last row all positive, then there is no 0 to the right of C. Okay, so when I try the C here is 6, right? And all the numbers underneath here are all positive. Now, if that's the case, then 6 is not a 0, and no number greater than 6 also 0. Okay, not even an irrational number, no. If you use synthetic division where this is 6 and positive numbers here, okay, then 6 is not a 0 and no number to the right of that greater than 6 is a 0. Okay, now, let's try 3 instead then. So we know 6 doesn't work. Let's try 3. Let me try 3. That will be 1, negative 3, negative 3, 7, 6. When I try 3, 1. This is 3, 0, 0, negative 3, negative 9. Oh, I think this will give us 0. Yeah, this is our 0. Okay, 3 is a 0. Okay, so I can go on from here. I can go on from here. Notice that what I did on the right-hand side were the one I did to the right of this are scratch work. Okay. And then the one you need to show me is the one on the left-hand side. 3 is a 0. Now this is degree of 3 because we basically have factored it in a way that px equals to 3 times x minus 1/3, x minus 3, x cubed minus 3x minus 2. Okay, now from here we can update our rational zero theorem again. Like this plus minus 2 and 1, right? So the C will be plus minus 1 or 2 over 1. Okay, so C will be plus minus 1 plus minus 2 only. Right? But we already tried positive 1, it didn't work. So if you still look for a positive 0, let's try 2 right now. Let's try 2 right now. Okay, let's try 2. So let me do it here. Let's try 2. So you see the scratch work is a lot more extensive, huh? So 1, 0, negative 3, negative 2. I don't know if 2 works though. I still don't know, but let me try it anyway. 1, this is 2, this is 2, this is 4, this is 1, this is, oh, it is. Okay, so let me copy that here. So 1, 0, negative 3, negative 2. When I divide by x minus 2, I get 1, 2, 1, 0. Okay. And then the last part, this is x squared plus 2x plus 1. Set it equals to 0. That's x plus 1 squared. So x equals to negative 1 with multiplicity of 2. So the zeros are x equals to 1/3, x equals to 3, x equals to 2, all with multiplicity of 1, x equals to negative 1 with multiplicity of 2. Okay, so px in factored form, in linear factor form, will be px equals to, the leading coefficient is 3, x minus 1/3, x minus 3, x minus 2, x plus 1 squared. Okay, and then the next question, I don't even remember what's the last one. Part C, now it's part D. The y-intercept, we have done it earlier, that's 0, negative 6. The x-intercepts are 1/3, 0, 3, 0, 2, 0, negative 1, 0. Suppose I want to sketch the graph. X-intercepts are 1/3, 0, 2, 0, 3, 0, and then negative 1, 0. Y-intercept is 0, negative 6. Degree of 5, leading coefficient, leading term, leading term is 3x to the 5th, right? Odd degree coefficient 1, so it must be bottom, top. You can do sine graph to actually get it though. Now, the thing is that at negative 1, it's multiplicity of 2, so it's bouncing. Okay, and then at 1/3, 0, it will cross because it's multiplicity of 1. At 2, 0, it's cross because multiplicity of odd multiplicity, and this is also odd multiplicity. So it will look like approximately that. Okay, that's what the graph looks like. Now, actually, you will see that if the degree is odd, maybe I write it in red here. No. If n is odd, then the range of that polynomial is all real numbers. Okay, that's something we don't have if it is degree of 2. Like when we have a quadratic function, the range is not all real number. It's only up to certain number or down to certain number. But once the degree is odd, you see that it goes to negative infinity on the left-hand side here, and it goes to positive infinity on the right-hand side there. Okay, so the far end behavior you will see will be top bottom or bottom top. In this case, bottom top. Only when the degree is odd. Okay, now let me give myself a break. Right now is 12:07. We take a break, we come back at 12:17. And that's the end of our polynomial discussion. Suggested homework from this 3.4. But don't forget, you have a homework due tomorrow. I think that's quiz 456 that we need to turn in by tomorrow. If you finish today, just turn it in today. Suggested homework from this 3.4 part B will be from number 19 to number 29. You may actually take a look on number 31. Number 31, but try not to look at the graph though. Okay? Yeah, try not to look at the graph. What else? I think that's what I want you to do. Okay, let me move on to 3.5. Now this 3.5 is a long section, very long, very long. I don't think that with only 2 hours I can finish this, but at least I can finish do the important key steps before we put things together tomorrow. Now this 3.5 is on rational function. And a rational function is defined to be, let me use Rx for rational function, is defined to be a function whose numerator is a polynomial and denominator also a polynomial. Now, for the purpose of our notation, I will use Px on the top and Qx for the denominator. Okay, and I will use coefficient a's on the top, degree n, because it's polynomial, right? So I still can use polynomial notation. Over, and in the denominator, I will use coefficient b's with degree m. M and n don't need to be the same. That's just for notation, help us with notation. Okay, now actually then what are the possible questions? What are the questions you need to be aware of possible here? The possible questions are questions we need to answer. The first one is the domain. Okay, let me do one by one. Okay, now how to find the domain? to find the domain of a rational function. The domain is all the x. The domain is all the x where qx is not equals to 0. Okay, basically the domain of a rational function is all the x which is not the 0 of the denominator, because it will make it undefined. Okay, so for example, if I have a rational function x squared minus 4 over x squared minus 5x minus 6. Then the domain will be, let's factor it out first. So when I factor it out, this will be x plus 2x minus 2 on the top. And at the bottom, we have x minus 6, x plus 1. Right? So the domain will be all real numbers except 6 and negative 1. Okay, I think this one is easy, right? I think this one is easy. I will do the following. I will do more topics. Like right now I do domain, I do the example, right? And then I will do more topics. Let's say, for example, the next topic I will do is the y-intercept. The y-intercept. And then I will apply this y-intercept into example 1 and example 2. I give you another example, okay? So let's say the y-intercept, let's apply that the y-intercept is 0, something. What is that thing? That thing will be a sub 0 over b sub 0. You will see when x equals to 0, then all of these actually disappear. All of these disappear when x equals 0, right? And we are left only with the constant over constant. Now, of course, you don't have y-intercept if b0 is 0. Right? If b0, b sub 0 is 0, then we don't have y-intercept. But you will detect that right away from the domain. So let's see, in our example 1, Rx equals to x squared minus 4 over x squared minus 5x minus 6. And the y-intercept is 0, negative 4 over negative 6, which is 0, 2/3. Let's see example 2. Let's see example 2. Example 2, suppose I have a rational function 3x squared minus 4 over 2x squared plus x. You see that the domain here is all real numbers. Let me factor that first, the one at the bottom. Let me factor the one at the bottom at least. Take the x out, so I get 2x plus 1, right? So all real number, the domain is all real numbers except 0 and negative 1/2. Now notice that 0 is not in the domain. Because 0 is not in the domain, then because 0 is not in the domain, then there is no y-intercept. Now you can try R0 is what? When you see R0, that will be R0 is negative 4 over 0. That's undefined, right? And if you think about it, it has something to do with the fact that the constant on the denominator is 0. Okay, that's for the y-intercept. Now the third topic is on the x-intercept. X-intercepts comes from the real zero. So you need to find the zero, okay, but the zeros has to be real number. The zeros of the numerator px comes from the real zeros of px. So to find the x-intercepts, you need to first find the real zeros of px. Now here's the logic. Here's the logic. Here's the logic. Now Rx, we set that equals to 0. Now it implies that to find x-intercept, we need to set the y equals to 0, right? Okay. Now, but it means px over Rx, I'm sorry, over qx equals to 0. Now a fraction equals to 0 only if the numerator is 0. Okay, that's where the logic coming from. But of course, we need to avoid that, be aware that cross out those x's, those zeros not in the domain. Not in the domain. Okay, cross out those zeros not in the domain. Okay, let's try. So if we look back to our example 1, Rx equals to x squared minus 4 over x squared minus 5x minus 6. So the x-intercept, basically, we look at the numerator. Okay, now, you know what, what we usually do, we factor it first, right? Let me factor it first. It's easier to see. So when I set this equals to 0, basically you will see that I need to solve this thing. Just the numerator. So we will get x equals to -2, x equals to 2. And both of them are in the domain, so x-intercepts are -2, 0, 2, 0. Now, the polynomial may get a lot more complicated that requires some skill in deciphering that. But that's something we learned in the polynomial earlier. Okay, now that's for example 1. Let's look back to our example 2. Our example 2 looks uglier. Or let me do our example 2 here. Example 2, our Rx equals to 3x squared minus 4 over 2x squared plus x. So if I ask for x-intercept, what I need to solve is actually 3x squared minus 4. Okay, set it equals to 0. Just the numerator, set it equals to 0. It's 12 over 9. I make the denominator a square so that it's easier for me. So that's plus minus 2 radical 3 over 3. Okay, so the x-intercepts, partition these. So x-intercepts are 2 radical 3 over 3 comma 0, negative 2 radical 3 over 3 comma 0. Now what happens if we have a 0 that is actually not in the domain? Let's do a new example. Our x equals to x squared minus 4 over x squared minus 5x plus 6. This will be x plus 2, x minus 2, x minus 3, x minus 2. So from here you see that first the domain is all real numbers except 3 and 2. Part B, the y-intercept is 0, negative 2/3, right? I mean, you plug this in, negative 4 over 6, and then you reduce. How about the x-intercept? The x-intercepts, you will see that it's supposed to be negative 2. The zeros are, maybe I put this here. So x plus 2, x minus 2 equals to 0. So x equals to negative 2, x equals to 2. But x equals to 2 is not in the domain, so I cross it out. Okay, it's not in the domain, so I cross it out. So the x-intercept only negative 2, 0. Okay, now I want to go on a bit from this function here. We will say that this Rx is equal to x plus 2 over x minus 3 for x not equals to 2, and it is undefined for x equals to 2. Okay, it is not correct. It is not correct to say that Rx, it is not correct to say that this Rx, which is x plus 2, x minus 2 over x minus 3, x minus 2, it's not correct to say that it is equal to. It's not correct to say it's equal to x plus 2, x minus 3. It's not true. It's not true. Okay, it's not correct to say that. This is only true when when x is not equals to 2. When x is not equals to 2, let's say x equals to 5, right? Then this guy will be 3, this will be 3, which later on they cancel, right? Okay, when x is not equals to 2, there will be the same number that cancels, and the result will be the same to this. But it is not true when x equals to 2. Okay, when x equals to 2, what happened? You see, R2 is undefined. But x plus 2, when I replace this x by 2 and then 2 minus 3, that's negative 4. Okay, they are not the same. They are not the same. Now, to be more detailed, let me use black color. In fact, x plus 2, x minus 2 over x minus 3, x minus 2 is equal to x plus 2, x minus 3 everywhere. They are the same everywhere except at x equals 2. Okay, now let me say the following. From now on, what we have here, I will call, that's the original rational function, right? Okay. Now the simplified one, I will call r star x. Okay. R star x. So basically, I want to say that r star x is the simplified version of Rx. Okay, now, why do I want to emphasize this? Because you will see, for us to graph Rx later on, we will actually graph R star x. That's what we will graph. Then we do adjustment. Okay, let me write it down. To graph Rx, we will first graph R star x. Then we do some necessary adjustment. Okay. Now, what kind of adjustment is that? Let's do a little example first. It's so little that I don't want to number it. Let's take a look on this example. Let's say I have a function fx equals to 1. The function fx equals to 1, if you don't know what the graph looks like, drop the class. Fx equals to 1 is a horizontal line. It's a horizontal line. Right? Y equals to 1. That's the graph. Now, I want to compare that fx with the following graph. Let's call it gx. So gx, let's make it x minus 2 over x minus 2. Now, how do we graph x minus 2 over x minus 2? Now, we know x minus 2 over x minus 2 is equal to 1 as long as x is not equal to 2. It will be undefined when x equals to 2. So what will the graph look like then? Yeah, the graph will look like the same to our fx, which is 1, except that when x equals to 2, there's a hole. When x equals to 2, there's a hole. Because when x equals to 2, the gx is undefined. Okay, now this is the graph of gx. This is the graph of gx. Now compare that with the graph of fx. Okay. So if you ask me to graph gx, I will graph fx first, and then I do the modification in which I remove one of the coordinate. We call that the whole. Okay, we call that the whole. Now, in this situation, if this is my gx, this will be my g star x, the simplified version. Okay, the simplified version. Now, with that said, then the coordinate of the whole will be g star 2. So you plug this 2 here, which is supposed to be undefined, but you put it there. Okay, so the coordinate of this hole here, the coordinate of this hole here is actually 2, 1. Okay. Now go back to our example 3. Our Rx is x squared minus 4 over x squared minus 5x plus 6. Which factor to be x plus 2, x minus 2, x minus 3, x minus 2. And we say this simplifies to be x plus 2 over x minus 3. This is our R star x. When x not equals to 2, it will be undefined when x equals to 2. So the question is then, what's the whole? Where's the coordinate of the whole when you remove this? When you cancel this, right? Okay, then we have a whole. But where's the location of the whole? And coordinate of the whole will be R star 2. So I plug in this 2 in here. Okay, that's 2 plus 2 over 2 minus 3, that's negative 4. So the coordinate of the whole will be 2, negative 4. And we will graph this function later on. Okay. I have to say that before we talk about this coordinate of the whole, I suppose to talk about some asymptotes first. Something called horizontal asymptote and vertical asymptote. Now the next discussion we will do are vertical asymptote first. So this is part D, I think. Yeah, part C, x-intercept. Part D. Before we lose track, let's list what we have learned. First one is the range. I'm sorry, the domain. Always do the domain first. Okay, every time you deal with rational functions, always pay attention to the domain. And keep in mind, the domain is one of the key problems in pre-calculus. Okay, part B, another easy question is y-intercept. Part C is x-intercept. Okay, and we have a side note about the whole. Not every rational function have a whole. Okay, but if we do, it must be because of this kind of branching. Okay, so, oh, by the way, going back to example 3, going back to example 3, when I graph this function later on, what I do, I actually graph R star. I graph R star, and then I remove this coordinate. I make it a whole. Okay, don't worry, we'll be back there. We'll be back there. Okay, now the next one is vertical asymptote. Vertical asymptote. A vertical asymptote is a vertical line, actually it could be more than one, is a vertical line to which the graph x float to infinity or negative infinity when x approaching that number. So that's a vertical line. Let's call that x equals to c, such that as x going to c, approaching c, then the graph will get to positive or negative infinity. So let's say we have this situation here. So let's say we have a rational function, and then I have vertical asymptote, let's say here. Let's say this is a vertical asymptote. Now then, the graph of the function will look like as the following. Let's say as it goes closer and closer to that blue line, it will go to infinity. Or if you approach from the right-hand side, maybe it goes to positive infinity, or it goes to negative infinity. Okay, it goes to, yeah, the closer you are to that x equals to c, okay, then the closer the graph to that blue line, to that vertical asymptote, but the graph will not touch vertical asymptote. The graph will not touch, or not to say to cross, it will not touch any vertical asymptote. Okay, now let's take a look on some possible graphs. Give me a second. Let me share with you, and I get from internet. Vertical asymptote. Now, this is vertical asymptote. Let me click this one. Let me click that one. Put it in. So you see that these are the vertical asymptote. This is vertical asymptote. This is also vertical asymptote. Okay, those are vertical asymptotes. Now the question is then, how do we find vertical asymptote? How do we find vertical asymptote? The vertical asymptote is given by x equals to the 0, now we will start with x equals because it's a vertical line, okay? The 0 of q star x, the simplified version of Rx. If you remember R star x, that's P, if I call the simplified version, P star x over Q star x. Okay, that's the vertical asymptote. Now, actually, you can see from this example here, from the graph I quote, notice that I cannot simplify that further. Okay, I cannot simplify that further. So the Q star and Q will be the same. Basically, we just look at the denominator, right? I cannot simplify that further. Okay, and then we say from here that the vertical asymptotes are x plus 3 equals to 0 means x equals to -3, and x minus 1 equals to 0, x equals to 1. Okay. Now, of course, vertical asymptote has something to do with the domain. It's all real numbers except -3 and 1, but not always, not always the same. In this case, they happen to be the same. X equals to -3, x equals to 1. But that's because nothing get canceled. Okay. Now, suppose I look back to my example 1. So we have seen that example 1 very, very well. Our x equals to x squared minus 4 over x squared minus 5x minus 6. Notice that nothing canceled, right? I mean, the simplified version and the original version are the same. Nothing canceled. So the vertical asymptote will be x equals to 6, x equals to -1. Now, however, if I compare that with example 3, in which I have Rx equals to x squared minus 4, x squared minus 5x plus 6. Now we say that this is equals to, the simplified version is x plus 2, x minus 3. Right? For x not equals to 2, it's undefined for x equals to 2. Right? Then what is the vertical asymptote? The vertical asymptote is x equals to 3 only, because we are not looking from here. No, not from here, but look at this one. Okay, we don't look at the denominator, the 0 on the denominator of the original function. No, we look at the 0 of the denominator of the simplified version. So Thomas, what happened when x equals to 2 though? When x equals to 2, it becomes a whole, remember? It does not becomes an asymptote. Okay. Now later on, I will show you the graph of all these functions. So all the functions that I showed you earlier. And hopefully from there, we can also see how we can sketch the graph ourselves. Okay. Maybe let's do that now. Let's do that now. Why not? Let's do that now. Give me a second. So let's go to my graphing paper. Y equals to x squared minus 4 on the numerator divided by x squared minus 5x minus 6. This is for example 1. This is for example 1. Copy the graph and then bring it back to our node. It's way too big. Let's make it a bit smaller. This is example 1. Let me write it down. This is the graph of example 1, where our x equals to x squared minus 4 over x squared minus 5x minus 6. Actually, we can confirm a couple of things though. The very first one that we can confirm is the vertical asymptotes. You see that x equals to -1 and x equals to 6. Those are the vertical asymptotes. On the top of that, you can also confirm that the y-intercept is positive 0, 2/3, and the x-intercepts are 2, 0, -2, 0. There's no hole here. The domain is all real number except the domain is all real number except the zeros of the denominator, which then in this case becomes the vertical asymptotes. Okay. Now, how about the graph of example 3, where I change the denominator, -6 becomes +6. Otherwise, it's too big for us to see. This is example 3, where Rx equals to x squared minus 4 over x squared minus 5x plus 6. Now, according to what we had earlier, we found out that the vertical asymptote is only x equals to 3. Now, what happened when x equals to 2? When x equals to 2, you see when x equals to 2 here, you have some, you see kind of like a missing pixel. Let me enlarge this. Let me enlarge this so that you can see the missing pixel. Do you see that missing pixel? Right? Okay. Now, so we see that's an empty circle there. That's the hole. Now, the coordinate of the hole we have found earlier, that's 2, -4. Right? Let's take a look at what we did some time ago. 2, -4. You see that? Oops. Here, for our example 3, the coordinate of the hole is 2, -4. Okay. And yes, we also found that the y-intercept is -0, -2/3. The x-intercept is -2, 0. That's confirmed, right? So we have the domain, y-intercept, x-intercept, a hole, and a vertical asymptote. Okay. Now, later on, we need to learn, after the break, we will learn how to get the above and below x-axis. But before then, we will need to do two things first. before then, we will still need to do two things. We still need to do, what was the last one? Vertical asymptote is part one. Part T. Vertical asymptote is part T. So part E, we will do horizontal asymptote. Okay, horizontal asymptote. And after we get the horizontal asymptote, we'll do the graph again. And then after that, we formally go to the graph. We will first do the sine graph before we do the graph. Now the sine graph, just like the way we did it before, sine graph help us to see if in that interval after the critical points, if it is above or below x-axis. Okay, more details coming though, more details coming. But let's take a break first. Right now it's 1:02. Let's come back at 1:12. Okay, let's start again. The next thing we will do is horizontal asymptote. Now, what is horizontal asymptote? If we look at this graph here, the horizontal asymptote for this graph happens to be hidden. I call it hidden because you can see it clearly at this x-axis, y equals to 0. While if we look at this guy here, the horizontal asymptote is actually y equals to 1. That's the horizontal asymptote. Now, horizontal asymptote is a horizontal line to which the graph is approaching as x going to infinity and x going to negative infinity. Okay, so it is possible that we don't have horizontal asymptote. Okay, it is possible. But if we have horizontal asymptotes, then the graph will go to approach that line, horizontal line, when x goes to, the further you go to the right hand side here, the closer you are to that line, and the further you go to the left, the closer you are to that horizontal line. Now, we can see also in this case here, the horizontal asymptote is also happens to be the same, y equals to 1. You see, the further we go to the right and the further we go to the left, the closer the graph will be toward that horizontal asymptote. Okay, now that's more or less the definition of horizontal asymptote. But I need to say that, so horizontal asymptote will be, if any, that will be y equals to constant. Okay, if any. So we have rational function that doesn't have vertical asymptote. We also have rational function that doesn't have horizontal asymptote. Okay, yeah. Now, so how do we find the horizontal asymptote? Now, it depends on the degree. Okay, horizontal asymptote. First, if the n is less than m, this is the degree of px, the one on the numerator, and this is the degree of qx. Then, if the degree on the top is less than the degree at the bottom, then horizontal asymptote is given by y equals to 0. For example, let me do a little example. Let's say, for example, if I have 2x minus 3 over x squared plus 4. Notice that the degree on the top is 1, the degree at the bottom is 2. When x is very, very large, when x is very, very large, then this will be large, but this will be even more large. Okay. Likewise, when x is very large negative number, this becomes large, this becomes even larger. So a large divided by something even larger, it becomes 0. Or we can do the algebraic manipulation that you will see in calculus, in which I will divide by x squared, the highest degree on the top and the bottom. So 2x minus 3, I will divide by x squared. And x squared plus 4, I will divide by x squared. This will be 2 over x minus 3 over x squared over 1 plus 4 over x squared. Now, as x goes to infinity and negative infinity, you will see that the top, this guy here will be 0. 2 over something very big is 0. 3 something over something very big is also 0. This is already 1, and this is also 0. 0 minus 0 over 1 plus 0, that will be 0 over 1, that's 0. Okay, that's the to find the horizontal asymptote. And yes, you can see that that way, as long as the numerator, the degree of the numerator is smaller, then the horizontal asymptote will be 0. Now, the second rule is what happens if they are same. If the degree on the top equals to the degree at the bottom, then horizontal asymptote is given by y equals to leading coefficient on the top over leading coefficient at the bottom. Okay, now we actually have seen that example here. You see that the degree on the top and the bottom for this example are the same. Okay, so the horizontal asymptote will be y equals to the leading coefficient on the top, which is 1, over leading coefficient at the bottom, which is also 1. Okay, so the horizontal asymptote is y equals to 1. And you can apply that also to other case. The first case, y equals 0, is this one here. You see on the top, the coefficient on the top is 2. I'm sorry, the degree on the top is 2, while at the bottom the degree is 3. Right? The 3 is like 1 from here, degree of 1 from here, degree of 2 from here. Okay, so the degree on the top, n equals to 2, m equals to 3. If the degree on the top is less than the degree of the bottom, then the horizontal asymptote will be y equals to 0. Okay? Now, what if then the degree on the top is more? If the degree on the top is more, then no horizontal asymptote. Now, this one you have to memorize. Okay, this one you have to memorize. Now, let me pick one problem at which we will work on whatever we have learned so far. Okay, whatever we have learned so far. So let's say, for example, I get example 4. Example 4, we have, let's say, Rx equals to x plus 1 over maybe 2x plus 1 over x squared. No, I don't like that. Cancel the 2. X squared minus 5x minus 6. which is equal to Rx equal to x plus 1 over x plus 1 x minus 6, which simplifies to be r star x plus, no, that's 1 over x minus 6 for x not equals to -1. And it is undefined and therefore becomes a whole, in this case, for x equals to 1. First part, the domain, is all real numbers except -1 and 6. Part B, the y-intercept is 0, -1 over 6. That's straightforward. Part C, the x-intercept. The x-intercept supposed to be x, the numerator, x plus 1 equals to 0, right? So x equals to -1. So x equals to -1. But this is not in the domain. So now we don't have an intercept. Okay, now we have a hole here. So find the coordinate of the hole. To find the coordinate of the hole, I put that x equals to -1 into the simplified version. 1 over -1 minus 6, that's -1 over 7. So the coordinate of the hole is -1, comma, -1 over 7. Now, how about the vertical asymptote? The vertical asymptote. We look at the simplified version and the 0 of the denominator. While horizontal asymptote, the degree on the top is less than the degree at the bottom, right? The degree on the top is 1, the degree on the bottom is 2. So the horizontal asymptote is y equals to 0. So let's put things together. Let's put things together as much as we can. The y-intercept is 0. I will draw it not with drawn to scale. I try, but not drawn to scale. 0, -1, 6. No x-intercept. The whole is -1. Let me graph the rest first. So the vertical asymptote is x equals to 6. Let's say it's here. This is x equals to 6. Okay, and horizontal asymptote y equals to 0, so it coincides to the x-axis. That's y equals to 0. Then how do we proceed from here if this is all we have? Let's do the sine graph. That's why you see that it's better for us to do sine graph first, right? The sine graph. The critical numbers are -1 and then 6 and then -1 and 6. At -1 it is undefined. At 6, I'm sorry, at 6, at 6 is also undefined. Okay, the y-intercept is negative, right? That becomes our testing point. And 6 is a critical number with multiplicity of 1. It's an odd multiplicity, so I change the sign. while -1 is a critical number with multiplicity of 2. It happens once at the top, once at the bottom. So it has multiplicity of 2. Now, because the multiplicity is even, then there is no change of sign to the left or to the right of the critical number. Now, these are negative means they are below x-axis. Positive means above x-axis. Okay? So far so good? Now, let's start. We know that the horizontal asymptote is y equals to 0, which means when you come from very far on the left-hand side, you will come from the horizontal asymptote. Now, but we don't know if it is above or below the horizontal asymptote. Well, I think I need to put a note that the graph may note the graph of Rx may intersect horizontal asymptote. You cannot intersect vertical asymptote, but horizontal asymptote is possible. So we don't know if we start from the top or the bottom, but from the sine graph, we know it's supposed to be below the x-intercept, below the x-axis. Okay, and then I will go all the way, and it becomes, because we get closer to vertical asymptote, then it will go to -infinity. How do we know it's not going up here, Thomas? How do we know it's not going up there? Well, because there's no x-intercept. You see, there's no x-intercept there, right? If that's the case, then we must have x-intercept, right? But why not then we start from the top and going up like that? Well, because the sine graph are negative, right? Okay, so not this. It's not going to positive infinity; it goes to negative infinity. And I need to put more detail here that when x equals to -1, I actually get a hole. Okay, I actually get a hole. So let me erase this part here. I actually have a hole there. If you want to put more details, you can find what is the value when x equals to 1, x equals to 2. But what I need to see are only these things. Likewise, when it comes from very far on the right-hand side, I will start from the horizontal asymptote. I know there's positive sign, so it's above x-axis. And as I get closer to vertical asymptote, then I know it will go to positive infinity. How do we know it's not going to negative infinity, Thomas? Well, if it goes to negative infinity, you will have an x-intercept there. But that's not what we have according to our theory. Okay? So it's not. It's not. Let's do other problem. Let's do other problem. For example, this example 5. Did I do all the problems for horizontal asymptote, vertical asymptote, the sine graph, the sine, and the graph? Okay, yeah. GFGH. This is the example 5. Example 5. Let Rx equals to 2x squared minus 5x plus 2 over x squared minus, let's say, minus 3x minus 4. I think nothing cancels here. Let's factor it first. Always, you need to factor it first. Always factor it first. Okay, so this is 2x x minus 2 plus 1. This is x minus 4 x plus 1. So factor it first and then find the domain. When you look at this example here, I would like you to pause a little bit and try to do this problem first. Okay, find the domain, the y-intercept, the x-intercept, vertical asymptote, horizontal asymptote, is there the hole if any, and then sine graph to help us graphing it later on, up or below the x-axis, and then to graph it. If possible, we may be able to answer this question later. Intersection with horizontal asymptote. So if the graph intersect horizontal asymptote, where will that be? What's the coordinate? Okay, now you can pause a little bit, try to do this first. Okay, for those questions that I consider easy to answer, straightforward, I will just answer right away in this space here. For the ones that requires more space, I will do it below. Okay, you can pause it first and start to work on that. Give yourself like 5 to 10 minutes to do as much as possible. Okay, but you will see the key is actually to factor them. Okay, so that the domain will be all real numbers except 4 and -1. The y-intercept is 0, negative 2 over -4, which is 0, -1/2. The x-intercepts will be, you see from the numerator, right? 2x minus 1, x minus 2, you set it equals to 0, so you get x equals to 1/2, x equals to 2. These are the zeros of the function, and because both of them are real numbers, they give us the x-intercept also. But distinguish the zeros and x-intercept. Okay, x-intercept must be a coordinate. Zeros may be complex number, non-real complex number. Now, but if your zero is a complex number which is not real, then it won't translate into x-intercept. Okay, only when the zeros are only when the zeros is a real number, like in this case, then it becomes x-intercept. Okay, so zeros and x-intercepts are very close, but they are not equal. They are not the same. Okay, vertical asymptote, the function is already simple, so we just get the x equals to the 0 of the denominator. There are two vertical asymptotes here. Now, don't forget that under no way, under no time, the rational function will intersect vertical asymptote. Okay, now how about horizontal asymptote? Horizontal asymptote, y equals to 2 over 1, because they have the same degree of 2, both of them. Okay, so once they have the same degree, we actually divide the leading coefficient over the leading coefficient. Okay, but make sure you write it as horizontal line. Okay, because no canceling here, we have no hole. Now, before I do the sine graph and the graph, let's do this one first. Let's do intersection of horizontal asymptote with the function. Now, horizontal asymptote, y equals to 2. Okay, now you set that equals to Rx, and then solve for x there. Okay, that's how we find the intersection of the graph with horizontal asymptote. Now, whatever the equation of horizontal asymptote, y equals to 2 in this case, and you set that equals to the y of the function, which is Rx. Okay, so if I go on further, this will be 2 equals to 2x squared minus 5x plus 2, and at the bottom we get x squared minus 3x minus 4. Now when we solve this, x squared minus 6x minus 8 equals to 2x squared minus 5x plus 2. 2x squared cancels. Okay, so I will get negative 8 minus 2 equals to negative 5x plus 6x. So x equals to negative 10. So the intersection is negative 10, comma 2. Okay, now let's do the sine graph. Part G, sine graph. Part G, sine graph. The critical numbers are 1/2, 2, 4, 2 here, 4 here, and then negative 1. These are the x-intercepts. These are the undefined. Okay, and then I do the sine graph. I know it will be like this because my y-intercept is negative. When x equals to 0, my y is negative 1/2. Right? So I use my y-intercept to help me with the sine graph between negative 1 and 1/2. And because all critical numbers are multiplicity of 1, then the sign will alternate. Now, usually we use the sine graph to solve the inequality, right? Now we go into a more general situation. We use the sine graph to help us doing the graph. The sine graph tells us where will the function be above or below the x-axis. Let's see. So the y-intercept 0, negative 1/2. X-intercepts are 1/2, 0, 2, 0. For vertical asymptotes, x equals to 4. And x equals to negative 1. Horizontal asymptote, I think, is y equals to 2. The horizontal asymptote y equals to 2. I don't draw it to scale. Okay, I don't draw it to scale. Then, what happened to the graph? Come from negative infinity, right? From when x goes to negative infinity, I go this way. Now the thing is, I don't know if it is above or below. I don't know if it is above or below. I know for sure that it won't be like this. It won't go down, because if it goes down, I must have an x-intercept there, which according to my computation, that's not the case. So it won't be that one. It won't be that one. And it must be the one, it must be the one from here, goes up. Okay, it must be like that. Thomas, hold on. Why don't you say, why can't we draw it this way, from below horizontal asymptote and it goes up? I think that's supposed to be the case. Yeah, that's supposed to be the case. Not the first one, not the first one, not this one. Should be start from below and then goes up. Now, how do I know? Because we have intersection with horizontal asymptote. It happens here. Okay, now then, furthermore, we know x equals to -1 is a critical number with multiplicity of 1, such that there's a change of sign. There is change of sign, okay, between to the left of -1, to the right of x equals to -1. So from, this is positive infinity here, right? And then this must come from -infinity going up. Yeah, follow the sine graph, okay? Follow the sine graph, and then you will see this actually go down. Okay, so between -1 to 1/2, it's below x-axis. From -1 to 1/2, it's below x-axis. Between 1/2 to 2, it's above x-axis. Between 2 to 4, it's below x-axis. Okay, and then from there we can say that to the right of 4, it will be positive. So it will be positive, positive. The thing is, how do we know, Thomas, is not coming from below the horizontal asymptote? Below horizontal asymptote and goes up like the one on the left-hand side, like the one on this side here. It won't be the case, because if that were the case, we must have detected the horizontal asymptote intercept there. But that's not the case. That's not the case. In fact, if you want to refine, the sine graph, the sine graph we did up here in part G is the sine graph for, this is sine graph above, to help us above or below x-axis. Okay, now with what we have right now, it's actually enough for us to see if it is above or below x-axis. Okay, and get the graph. But if you want to refine, make your work even more complete, you can do the sine graph with respect to horizontal asymptote. So what you do is, in the last couple minutes, like 14 minutes, if we want to get an even more detailed analysis of the graph, either it is above or below horizontal asymptote, what you can do, you do the following. You do Rx minus the horizontal asymptote and call that a new function. Okay, our x equals to minus horizontal asymptote, and call that a new function, and then you find the sine graph. Do the sine graph of this new function fx. But you will see this is actually not necessary. If you think about this a little bit, you should be able to already tell with what we have right now, which part or which section of that graph, in this case the red color graph, will be above or below x-axis and above and below horizontal asymptote. That's actually good enough. Okay, that's actually good enough. The sine graph we have up here is the sine graph above or below x-axis, right? And once we get the intersection with a horizontal asymptote, then we know that there must be an intersection here and nothing else. So when we come from far left, we must start from horizontal asymptote. We just don't know if it is from above or below, right? Okay, but because we know that it will be positive here, goes to positive infinity here, and have intersection here, then this must be below here. That's the only way. Okay, that's the only way. But again, if you are interested in finding the sine graph above or below horizontal asymptote, what you can do is you do what you do this thing here. Okay, now let me put some detail into that. So let fx equals to 2x squared minus 5x plus 2 over x squared minus 3x minus 4 minus horizontal asymptote 2. So I get 2x squared minus 5x plus 2 minus 2 times x squared minus 3x minus 4 over x squared minus 3x minus 4. Fast forward, the 2x squared on the top cancels. I will get x plus 10 over x minus 4 x plus 1. You see the critical numbers will be negative 10, negative 1, and 4. Will be undefined here, undefined here, positive, negative, positive, negative, will be 0. Now this 0 means intersect with horizontal asymptote. This is when the rational function equals to the horizontal asymptote y equals to 2 in this case. The interpretation will be that if it is negative, means below the horizontal asymptote, and if it is positive, means it is above horizontal asymptote. Okay, I already did the graph, and you can compare with my sine graph here. To the left of negative 10, it's below. Between negative 10 and negative 1, it's above. Right? Between negative 1 and between negative 1 and 4, it's below the horizontal asymptote. And to the right of x equals to 4, that's above the horizontal asymptote. Okay, so we use analysis that we learned before to we use our algebra to graph. Okay, so do not rely on graphing calculator. You are not supposed to use graphing calculator anyway. Okay, but I promise you one thing: if you use graphing calculator, your graph will be it will distract you so badly, such that you don't know what they are actually. It's impossible. Therefore, it's impossible for you to find to get the graph without get all the ingredients first. Okay, the y-intercept, x-intercept, horizontal asymptote, vertical asymptote, okay, the sine graph, before you get the graph. Okay, the last one that we did here to find horizontal asymptote intercept. Usually being asked, but I never ask if it is above or below horizontal asymptote. Okay, so the red one here, the one here is a common, I ask that once in a while. Assume I will ask that. Okay, okay, but the one far below here, I never asked that, but it will be quite helpful if you can work it out. Okay, now I am about to prepare you for tomorrow. Something called slant asymptote. Slant asymptote, or also called oblique asymptote. Now, slant asymptote or oblique asymptote is a line which is not vertical, not horizontal, to which the graph, it kind of like behaves like horizontal asymptote, but this time you slant it. Okay, so let the blue one be a vertical asymptote. I mean, the red one be vertical asymptote, and then the blue one be slant asymptote. So your graph, let's say your graph may be something looks like this. Your graph may be something come from very close to the slant asymptote, and then let's say it goes to here. Okay, and then from the vertical asymptote, and then goes here. Okay, so we can say slant asymptote or oblique asymptote is basically just a slanted horizontal asymptote. Is there anything called slanted? No, I call that slant horizontal asymptote. Okay, now how do we find that? Slant asymptote exists if degree on the top is exactly one more than degree at the bottom. So you will see if the degree on the top is one more than the degree at the bottom, then you basically have slant asymptote, and of course no horizontal asymptote. Let's say for example, we'll do focus on this more tomorrow. Let's say for example, if I have 3x squared plus 4 over let's say 2x minus 1. Now you see that the degree on the top is one more than the degree at the bottom. Right? The degree on the top is one more than the degree at the bottom. Then no horizontal asymptote, or because the degree on the top is more than the degree at the bottom. But we have a slant asymptote because the degree on the top, which is 2, is one more than the degree at the bottom, which is 1 plus 1. Okay, and how to get the slant asymptote? How to get, so once we know there's a slant asymptote, how to get the slant asymptote of a rational function? And the answer is divide it and get the quotient without the remainder. Okay, so in this case, we can do the following. Suppose you can do a long division. 3x squared plus 0x plus 4 divided by 2x minus 1. Okay, 2x times what? 3x squared, 3 over 2x. So this will be 3x squared minus 3 over 2x. Divide, I subtract, I get positive 3 over 2x plus 4. And 2 times what gives me 3 half? That's plus 3 over 4, I believe. So this is the remainder, right? But we don't care about that. We just need this thing. So the slant asymptote is given by, it is an equation of a line. So I need to use y equals to 3 half x plus 4. Now I will stop here for now. I will continue tomorrow. Okay, I will ask you to do problems which, in my opinion, is doable already. Okay, and some theoretical problem, okay, notational problem. So from 3.5, I'll call it 3.5a. I would like you to do number 3, number 5, number 7, and number 9. I don't know if number 9 is difficult. I think it's okay. And then the one involving graphing, the number 11, do number 13 right away. Number 13, 15, compare that with number 17. You kind of like do both of them and see where's the difference. Number 19. I don't want to give you too much, but at the same time, you need to study. And number 25. Number 31. Maybe number 27 first before. So how many questions here? 7, 11. The first 4 are actually quite simple ones. And number 13 and on, you need to answer the question that the domain, y-intercept, x-intercept, vertical asymptote, horizontal asymptote, slant asymptote, and if any intersection, and also the sine graph, and then the graph. Okay, that's for today. See you then tomorrow.